Good morning, students.
Good morning, ma'am.
One request, those who didn't pay the fee, please submit the undertaking form, at least by today. I have received 6 responses only. Anyway, I don't know who didn't pay it. Okay, so I'm asking you, those who didn't pay the fee yet, please submit the undertaking form immediately. Okay, so coming back to our class, last class we have seen addition and subtraction algorithm on sign magnitude data. Okay, so sign magnitude data, what you have observed in sign magnitude data, the sign and magnitude need to be considered separately for operation. Okay, so due to this reason we have gone through 8 possible operations for addition and subtraction with different signs of our numbers, and based on the conditions of the signs, some cases addition of the magnitude is happened, some cases subtraction of the magnitude is happened. Okay, so by considering this, we have developed an algorithm, and it is concluded that the hardware requirements are 2 registers with the names A and B of n-1 width. So this is n-1 width registers and 1 bit flip-flops for storing the signs of the 2 numbers, first number and second number. After that, one complementer helps to get the complement of B register to perform the subtraction with the help of parallel adder whenever we require to perform subtractor, whenever we require to use subtractor. Okay, otherwise the mode control will decide to perform either A plus B or A minus B. Okay, after performing A minus B, the whatever extra bit coming out, which will decide the comparison between the magnitudes, whether it is A greater than B or B greater than A less than B, based on the conditions. If E is equal to 1, it is A greater than B, and you have to neglect the extra carry out, and whatever is the result available in the magnitude, we are using the same register for storing the result, right? So this is the correct result. If E is 0, it means A less than B, and we did 2's complement addition, so it says that the result is negative. So you have to complement this to get your original result. So A is replaced with A bar plus 1 whenever E is equal to 0. Okay, so this we have retrieved. And about the sign, if A greater than B, AS itself is the sign of the result. If A less than B, complement of the AS will be the sign of result. Okay, since whichever the magnitude is high, for that will be taken as a resultant sign. Okay, so this is what the algorithm that we have gone through, and this is the flow chart, right? So we'll see 1 or 2 examples, and then we move to another type of data, signed 2's complement numbers. Okay, so here let us consider 2 numbers, any 2 signed numbers. So please tell me on which we apply this algorithm and we try to get the result. Any 2 signed numbers.
Minus 10.
Any 2 numbers, you please tell me.
Minus 10.
Am I audible?
Yes, ma'am.
Dear students, please respond.
Minus 10,
Yes,
ma'am.
Okay. Sorry, my mic is on mute. That's why this speaker is on mute. Okay. Now tell me any 2 numbers, please.
Minus 10, ma'am.
minus 10
plus 3.
plus 3. Okay. So here we have to separate what is AS, what is A, what is BS, what is B. Okay. So what is AS? This represent sign component of your number. Okay. So AS is
Negative.
1, right? Negative. So it is 1. And A, this gives the magnitude component of the number. So my number is minus 10. In sign magnitude representation, sign is separate, magnitude is separate. So AS is 1, that represents the sign. Now A is the magnitude, magnitude is 10. So 10 in binary, how can you represent?
1 0 1 0.
1 0 1 0. Okay, right? So here our n minus 1, our n minus 1 is 4, right? Okay, so I require minimum 4 bits to represent my magnitude. So I am taking my n minus 1 number of bits in my register A should be n minus 1, that is equal to 4, and 1 sign bit. So totally length of your number is 5 bits as per here problem. Okay. Now coming to B, what is BS?
0.
0. And what is B? Magnitude
0 0 1 1.
0 0 1 1. Okay, right? So these are the values of AS and BS. Now you have to perform the operation, XOR operation between AX and BS, right? What is the output? Both are different, so it is 1. And what is the operation that you want to perform? You want to perform addition of these two or subtraction of these two?
Addition.
Yes.
Addition.
Okay, so if you want to perform addition, okay, so in case of addition, so add operation, you have to go by this flow chart, right? So add operation, my addend is in A, my addend is in B, and I have performed XOR operation between the signs. We got it as 1. It means different signs. So when the signs are different, I have to go by subtraction. Okay, right? So this flow in this path you have to come. Now what you have to do? You need to perform addition of 2's complement value of B to A. Okay, right? So I have to now calculate B bar plus 1, right? So what is B bar? B bar, B is this value. It's B bar is 1 1 0 0, 1's complement. Now B bar plus 1 is 1 1 0 1, right? And you have to add A to B bar plus 1. A is 1 0 1 0, B bar plus 1 1 1 0 1. Now add these two. 0 1 is 1, 1 0 1, 1 0 1 1, 1 1 is 0 and 1. You got this is what, where it is stored? It is stored in E flip-flop extra bit out of n minus 1 bit register. Okay, so where this result is stored, this will be replaced in register A. Okay, in register A, result is updating. I am using one of my input register for storing my result back rather than going with one more extra register, which will consume number of registers, right? Now based on E, here what you got? Here my E is 1, so I have to go by this path. Okay. So I have come by this path and my E is 1, so I need to go by this path. So since E is 1, it means A is greater than B, and my result is not equal to 0. So I can complete my operation where, so what is your A here? A is available in the magnitude, the result of magnitude, and AS, whatever it is there in AS, that will be the resultant sign. Okay, right? No changes to AS and A. So AS is equal to 1. Okay. So now complete, your result is 1, 0, 1, 1, 1. Okay. So your result is also in sign magnitude form, because your inputs are in sign magnitude form, and we will be getting the result is also in sign magnitude form. What is this value? So this represents the sign.
-7.
So minus, and magnitude is 7. So minus 7. So that is what we are expecting. Minus 10 plus 3 is minus 7. Okay. Is this clear? Similarly,
Yes, ma'am.
you can see all the possible cases. 10 minus 3 addition. Okay. Or 10 plus 3 minus 10 plus of minus 3. All possible 4 cases. You can go any of these wing. It will reaches to the end point. Okay. So this is what sign magnitude method of addition and subtraction, right? So do you require any another example, or else shall we move
No,
to
ma'am.
next topic? Okay, so we'll move to next topic. So in this, while developing algorithm, so we have gone through a procedure of separating the sign and magnitude. Okay, so you have to treat sign separately and magnitude separately. Okay, that is the difficulty in sign magnitude form, and you need to care about, you have to take care occurrence of only plus 0. So minus 0 need to be eliminated because it gives two different representations. Okay, so that also need to be taken care. Okay, these two are the complex, I mean, I can say difficulties while developing the algorithm. It makes the procedure lengthy. Okay, so now rather than going in this way, now if we go by sign 2's complement data. Okay, so here my numbers are represented in a 2's complement form. So in 2's complement form. Okay, so consider the same example that we have seen now. It is, we want to perform plus 10 in and plus 3. Okay, an addition between minus 10 and plus 3 I want to perform. So how you can do this in 2's complement form? Okay, so here my numbers need to be represented in 2's complement form. My number, first number is minus 10, right? So how to represent this minus 10 in 2's complement form? What is its value in its 2's complement form? See, first number is minus 10, second number is 3. Okay, so 3 means it is plus 3. So plus 3, how can we represent this? 0, 1, 1. Am I right? 0, 1, 1 is plus
Yes,
3.
ma'am.
Okay, I want minus 10. Because my number is a negative number, so I have to go by complements. The available complements, 1's complement or 2's complement, or else sign magnitude form. But I am using here 2's complement representation. So go in this method, right? So minus 10 need to be represented in 2's complement way. So to do so, first you have to take plus 10, right? What is plus 10? 10 is 1010. Okay, right? This is not plus 10. This is just 10. Okay, I want plus 10. So this is plus 10. Most significant bit should be 0. Then only I can conclude that the number is positive. Right? So this is plus 10. Now you have to take 2's complement of it. So first to take 1's complement, 1 0 1 0 1, and then add 1 to it. Okay, so you have to add 1 to it. By adding 1, 1, 1 is 1, 0, 1, 1, 0, 1. So this is what your minus 10. Minus 10 is 1, 0, 1, 1, 0. Am I clear?
Yes, ma'am.
Okay. So how many number of bits here? 1, 2, 3, 4, 5. My n is here 5. N is 5 here. First number is 5-bit length. So obviously I have to take second number is also 5-bit length. Whichever is maximum, that many bits we will take. So plus 3. 3 bits are sufficient. So whatever be the most significant bits will be zeros. Am I right? So this is
Yes,
my
ma'am.
plus 3. Okay. So now I have to perform plus 10 plus of plus 3. So I have to take plus 10. Sorry, minus 10. Minus 10 is 1, 0, 1, 1, 0. And then plus 3, I have to add 0, 0, 0, 1, 1. So this is 1, 1, 0, 1, 0, 1, 1. Okay. And do you get any carry here? There is no carry. E is 0. And what is the most significant bit? Most significant bit is 1. It means the result is negative. Okay. So this is what the result. Since we got most significant bit as 1, it means that the result is negative. So to get its corresponding decimal value, what should I do? I have to 2's complement this, then I will be getting the correct result. Okay. So 11001 is your result. To get its corresponding decimal value, I have to 2's complement it. 1's complement is 00110. Add 1 to it, I'll be getting 00111. So which is nothing but 7. I got the magnitude 7 after 2's complementing the result, means the result is negative. So minus 7 is your output. Okay, is that correct? Minus 10 plus 3 is nothing but minus 10. Minus 10 is represented as 11001 in its 2's complement way because it is negative number. Since my inputs are in 2's complement representation, so output will also be in 2's complement representation. So your output register, which holds the result, will gives you this is the value 11001 is the result. Okay. While performing the same addition, if you have a carry as 1, if you get a carry 1, we just neglect this carry. Okay. So that will be occupied in overflow bit, V bit. Okay. Right. So this is a simple addition. How we perform in 2's complement method. Addition or subtraction is in the same way. Right. So to perform this operation, I require a hardware with 2 registers. One register is called AC, accumulator register AC, which holds the total n-bit length of the number, not just the magnitude as if like in a sign magnitude form. Okay. So it holds the total n-bit length number including the sign. And the BR also hold the total n-bit length including the sign. Okay. And while performing the operation, we are not separating the sign. Okay. Right. And how we are doing? We are adding these two or complementing the second number and adding to the first number based on the operation. Okay. Right. So if the operation is plus, then we directly add. If the operation is minus, then the second number will be 2's complemented and then added. Okay. And whatever is the result, that will be transferred back to the register accumulator, which override the one of the input. And the extra carry coming out will be occupied in the B flip-flop. Right. So that is very minimum hardware. 2 registers which store 2 n-bit numbers, 1 complementer whenever required, If the operation is subtraction, we require a complementer. If the operation is addition, we don't require the complementer. And one n-bit parallel adder that adds the corresponding n bits of these two registers, and the result is overwrite back to the accumulator register, which holds the previous one of the input. Whichever is the extra carry bit that is coming out of V, available in V. Okay, so this is a simple algorithm in 2's complement method. Coming to the flow chart. So this is addition and this is subtraction. See, in addition, our first input again is in accumulator and added is in BR register, and we add these two, whichever is extra bit that will be occupied in V bit. We call that as overflow. And it is end. Finished. Our result is in accumulator, including the sign. Okay. And subtraction case, we call the terms as minuend and subtrahend. Minuend in accumulator and subtrahend in BR register, and we have to complement the BR register and then add it need to be added to the accumulator, since our operation is subtractor. Okay, you have to perform A minus B. So minus B is done by using the complementer, which gives us the 2's complement of B, and that is added to AC. The extra bit is available in V and finishes the algorithm. Okay, right? So this is algorithm for addition and subtraction with 2's complement data. So what are the advantages that you observed while deriving the algorithm is, we won't separate the sign bit while performing the addition, right? Okay, and anyway there are no multiple representations for any number. So minus 0 taking care, that is also avoided in this algorithm. Okay, right? Okay, so we have done example for addition, and I want to explain the algorithm example for subtractor also. So let us take example for subtractor. So my same numbers minus 10 and plus 3, I want to perform subtraction. Okay, so we have calculated our accumulator is minus 10 as how much we got. It plus 10 is 0, 1, 0, 1, 0. Minus 10 is 1, 0, 1, 0, 1. And
1, 1, 0.
How much is this? 1, 0.
1, 0, 1, 1, 0. 1, 1, 0.
1, 1, 0. Okay, this is minus 10. And your BR register is plus 3, which should take as the same n bits 0, 0, 0, 1, 1. Okay, so now I want to perform the subtraction. So I have to take 2's complement of 3 and then add it to A, BR. Okay, so BR 2's complement chesi dan A ki add cheyali. So 2's complement means BR bar plus 1. Okay, so minus 3 it means. So first take 1's complement and then add 1. So I'll be getting 1, 1, 1, 0, 1. So now I have to add AC plus BR bar plus 1. Right? So this I need to do because my operation is subtractor. So AC is 1, 0, 1, 1, 0 and BR bar plus 1, 1, 1, 1, 0, 1. So these two need to be added. It is 1, 1, 1, 0 and 1, 0, 3 ones, 1 carry and 1 result. Okay. So while performing 2's complement addition, whatever is the extra bit that we come, that it will be neglected. Anyway, it is stored in V bit. Anyway, we will neglect that. And this is what the result. So what is your accumulator holds? Accumulator holds 1, 0, 0, 1, 1. This is the result. Is this correct? So to get it, to justify whether it is correct or not, what you are expecting, minus 10 minus of plus 3 is, my result should be minus 30. Okay, so is this represent minus 13? Are you
Yes, ma'am.
okay? So to get its corresponding decimal value, take first ones complement. This is ones complement of this, and now add 1 to it. So I'll be getting 0, 1, 1, 0, 1. Apply powers of 2, which we'll be getting 13. And we did this magnitude after 2's complement. So add negative symbol to it. Okay. So minus 30. Right? So very simple operations, even in if my data is represented in 2's complement method. No need of separating the sign and all. Okay. So hence our computers are following only the 2's complement representations. Right? Okay. So is there any doubts in addition and subtraction algorithms in both types of data?
No, ma'am.
Okay.
No doubts.
If so, then we move to next multiplication algorithms. You now tell me how multiplication is carried out. Whenever two n-bit numbers are given and we want to perform multiplication of those two, how can you do that? See, whatever is the procedure that we are following, and we will implement that in terms of algorithm in the computer by using the hardware, right? So first of all, we should be clear with how we will do the multiplication operations. Okay. So multiplication of two fixed point binary numbers. In both the cases, we will see representing in sign magnitude and sign 2's complement. Okay, so in both cases, we will derive the algorithm anyway, right? So first, let us see sign magnitude representation. So one number is represented in two numbers are represented in sign magnitude form. We call first number as multiplicand, right? And second number as multiplier. And the result of multiplication is said to be the product, right? Okay. So let us consider I have two numbers plus 23 and plus 19. Okay. Right. So these two are represented in sign magnitude. How we will do manually? See, I have
We first multiply with 9 and then
19. So I will go by first digit 9 3s 27. 2 is my extra bit. 18 207. We call this as first partial product. Am I right? This
yes,
is not a total product. This is the first partial product. After that, next 1 into 3. And where you have to keep that 3, you need to keep that 3 by shifting left side by 1 bit after the first partial product, right? And then 2. After that, we have to add these two. 7, 3, 4. This is your final product. This is your second partial product. And this is our final product, total product. Okay. So how many partial products we have? 2. That is completely depending on this number or this number. Number of partial
On
products.
19.
On 19 means on multiplier, right? So based on the number of bits in my multiplier, the number of partial products will be differ, right? So if I have n digit multiplier, I'm having n partial products. Okay, so this is how we'll do in decimal. Similarly, if I want to do it in binary, so I have to represent this in binary. So which method I am following? Sign magnitude notation. So what is plus 23? Plus 23. So here I should use two registers, one flip-flop for storing the sign of multiplicand and another register for storing the magnitude of the multiplicand. Magnitude is 23. So it is 1, 0, 1, 1,
1, 1, 1.
Okay, this is about multiplicand. When we talk about multiplier, my sign bit, which is BS, it is 0, and my magnitude of multiplier is B, which is nothing but plus 19. Okay, so it is 19, 1, 0, 1,
0, 1, 1.
0, 1, 1. Okay, so in sign magnitude representation, while performing the operations, you have to separate the sign. So we are separating the sign and we are considering only magnitude for my operation. Okay, so now I have to perform A into B, nothing but 1, 0, 1, 1, 1 into 1, 0, 0, 1, 1 you have to perform. Okay, once you get the product, then based on this AS and BS, if both are same, what is the result of the product? If both are positive, result of the product is
Positive.
Positive.
Both are negative,
Positive.
Positive.
even then result of the product is positive, right? If both are opposite, the result of product is negative. In that way, we can decide finally. We can assign sign for the product. So first you have to get the product. Now the same procedure, whatever you are following for decimal, the same we follow even for the binary. We start with the first least significant bit, right? Please follow the algorithm procedure, because the same procedure we will implement in terms of algorithm. Okay, so this is the first bit that has to be in the multiplier, which bit? This corresponds to the least significant bit. Okay, so if you need to multiply this with the multiplicand, and if this bit is 1, the total multiplicand will result as the partial product. Am I right?
Yes.
This
Yes,
is the
ma'am.
first partial product. After that, we will remove this bit, and we have already considered, so neglect that bit. Next bit we need to consider, and if the bit is 1, then the total multiplicand will be treated as a partial product. And how I have to use? I have to shift the partial product right side by 1 bit. Okay, so the new partial product have to be shifted. Sorry, which side? This is left side. Okay, am I correct? So new partial
Yes, ma'am.
product has to be shifted left side by 1 bit, and then place your second partial product. Okay, after that, inspect the next subsequent bit. If it is 1, then it will be resulted, otherwise zeros. Okay, even the zeros, how you have to place? By shifting it by 1 bit left, you need to place. Am I right?
Yes.
Yes, ma'am.
Similarly, next digit 0, that also you have to use in this way. And last bit 1, so it is 1, 0, 1, 1, 1. And finally, you have to add all the bits. How many partial products we have? How many? 1, 2, 3, 4, 5. 5 partial products, because the multiplier is having n bit length, which is nothing but 5. So 5 partial products we have. Okay, so nothing but 5 times we'll be getting either multiplicand or all zeros. Okay, once you get all the partial products, Then we perform addition of these all. So here the only one is there, directly we next we have 2 ones, which is 1 0, and next we have 4 bits 1 1 1, which corresponds to 1 1, and next we have 5 bits, out of which 2 are ones, so 1 0, and then 3 ones 1 1, again 3 ones 1 1, it is 1 0 1 1. Okay, this is your result. Okay, so you have to apply powers of 2 to get the output to power 0, to power 1, to power 2, to power 3, to power 4, to power 5, to power 6, to power 7, to power 8. 64 plus sorry, it's 2 power 8 is 255. 255 plus 128 plus 32 plus 16 plus 4 plus 1, which is equal to 437, because we have 1 in the least significant bit, so it is an odd number. Our result is 437. It is correct. Magnitude is correct. Okay, right? So this is
Yes, ma'am.
by observing this procedure. So what we are doing, we are looking at the successive bits of the multiplier by considering least significant bit first, right? If the multiplier bit is 1, the multiplicand is copied down. Otherwise, zeros are copied down. Okay. So numbers that we are copying down, successively, they are shifted 1 bit position to the left from the previous number. Okay. From the previous number, successively the numbers we are writing down are shifted left side. Am I clear? Finally, all these partial products are added and their sum forms the total product. Okay. Of course, the sign of the product is determined from the signs of the multiplicand and multiplier. If they are alike, the sign of the product is positive. If they are unlike, the sign of the product is negative. Right? So by observing this, can you tell me to implement this in digital computer, what about the hardware that you require? See,
Registers.
2 registers that holds the multiplicand and multiplier, right? A and B. And what about the product? See, here it is 5 and 5, right? And here what is the
Yes,
result?
ma'am.
How many bits are there?
9 bits.
9.
9 bits.
But there is a possibility of getting one more bit. Sorry, these are 9 and one more bit, which is nothing but the sign bit combinedly 10 bits. Okay, if I have n bit, 2 n bit numbers are multiplied, I'll be required 2n bit register for storing my result. Okay, right? So I will do some changes in my process so that it is convenient to implement in a computer. So first is A and B, which are of 2 n bit registers. So I'm using the same registers A and B combinedly, which is used for storing my product. Okay. Okay. Right. And whatever is there, whatever is available, which register, whichever is holds this multiplier, the corresponding least significant bit. Okay, so corresponding least significant bit, every time you have to inspect so that the carry, the multiplicand, whichever is there, that will be copied down, or all zeros are copied down. Okay, right? And then, so we require a 2n registers for storing the product, and then after that, whatever are all the partial products that have to be added. See here, sometimes only 1 bit, 2 bit adder, 3 bit adder, 4 bit adder, 5 bit adder. Okay, so there are different adders different bit adders I may require. So rather than this, what can I do means I will add the partial product to a register which is initially 0. Okay, so we are accumulating the partial product rather than waiting for all 5 products and then adding, right? It is convenient whenever one partial product is there, then I will add that product to a register which holds the final output, which is initialized at zeros first. Am I clear? So first product is partial product is 10111. I will add this to a register which is initially 0. So then it results 10111 in that register. Okay, I'm going by accumulating the partial products rather than adding all the partial products at a time. Okay, because to implement this in a computer, I may require different bit adders, right? Based on the n bits, based on the bit length of your number. Is that clear? The second change.
Yes, ma'am.
Okay, so I'm accumulating the partial product. And second change, next change, see, once you get this next subsequent partial product, this next subsequent partial product has to be shifted left side by 1 bit before adding. Am I right? So before adding to the previous accumulated result, the partial product have to be shifted left side by 1 bit. Okay, so while implementing it in algorithm, what I will do, rather than shifting this partial product left side by 1 bit, I will shift the accumulated product right side by 1 bit. Now the same will be in a successive positions, correct positions. Am I clear?
Yes,
I will
ma'am.
shift the accumulated product right side by 1 time rather than shifting the partial product left side by 1 time. Okay, and then I will add the resultant partial product to the accumulated product. Okay, this is the next change. And third change, see, I have to add the multiplicand, right? I have to add every time the multiplicand to the accumulator if the least significant bit, if the bit that is inspecting in B register is 1. Okay, so if my bit in the multiplier, whichever we are inspecting, if that bit is 1, I have to add multiplicand to the accumulator where my accumulator holds the partial accumulated results. Okay, and then after adding, I will shift that accumulator value left side by 1 bit. Okay, if my inspecting bit is 0, do I need to add anything to the accumulated result? Because all zeros adding is nothing change in the magnitude, right? But you have to shift right side by 1 bit. This shifting has to be done. Am I clear?
Yes, ma'am.
Okay. So every time you have to inspect one least significant, from least significant bit, all the n bits need to be inspected in the multiplier. If the bit is 1, then multiplicand is added to the accumulator, which was initially 0, and then it is shifted by 1 bit. If the bit is 0, then the accumulator will be shifted right side by 1 bit without adding anything, because my multiplier bit is 0. You no need to add the multiplicand to the accumulator. So hence by going this way, at the end, after inspecting all the n bits of my B, I will be getting the required output in your accumulator, which should hold a possibility of to n bit width. Okay, is this clear?
Yes, ma'am.
Okay, So how many times this iteration has to be done is depending on the number of bits in your B. So here we have 5. So my iterations are 5. Okay, right? So I require one more register that specifies the number of iterations. Okay, right? So this is the hardware required. So okay, multiplication of two fixed point sign magnitude data. So this is what example we have seen, 23 and 19. These are the magnitudes. So these are the corresponding values and the partial product, so final product. Okay. So looking at this successive bits of the multiplier, LSB at first. If the multiplier is 1, the multiplicand is copied down. Otherwise, zeros are copied down. Okay, the numbers copied down in successive lines are shifted 1 bit position to the left from the previous number. Finally, the numbers are added and their sum forms the product. The sign of the product determines the sign of the multiplicand and multiplier, right? Based on the sign of the multiplier and multiplier. So now what are the changes for that we have implemented for hardware implementation? So instead of providing registers to store and add simultaneously, see, you have to store these many, you need to use these many registers that stores the partial products and finally they have to be added as per the procedure. Okay, so rather than using these many 5 registers for storing the partial products and finally adding, rather than that, okay, so it is convenient to provide an adder for the summation of only 2 binary numbers and successively accumulate the partial products in a register. That's what we are doing. Okay, so we use a register that accumulates this partial product every time adding. Okay, successively adding only n bit adder I will implement now, right? So that is the first change. And second change, instead of shifting the multiplicand to left side, the partial product is shifted right side. Okay, so here this is what the multiplicand that we are writing down. So instead of shifting the multiplicand left side, whichever is having the accumulated product, that will be shifted right side. Okay, right, which results in leaving the partial product and the multiplicand in the required relative positions. Okay, see, shifting this multiplicand left side or shifting this accumulator to right side will leave, any of the cases will leave the relative position of the bits. Okay, right? So there won't be any wrong in additive result. Next, when the corresponding bit of the multiplier is 0, there is no need to add zeros to the previously accumulated product. We call that as a partial product, since it will not alter its value, right? If the multiplier is 0, you no need to perform the addition of all zeros with the previously accumulated product. Okay, so just shifting it by right side 1 bit is sufficient. You no need to perform addition if the multiplier bit is 0. Okay, so these are the 3 changes that we have implemented in hardware, right? Coming to the hardware required. See, in A register, A and AS and A, this is the partial accumulator. We call this as an accumulator, which holds the result. Okay, initially these are zeros based on the number of bits of your multiplier, both are. Based on these two, the number of bits in accumulator is zeros. Okay, and B register holds the multiplicand. Multiplicand is available in B register. Its corresponding sign is in BS flip-flop. Okay. And multiplier is available in Q register. Okay. So multiplier is in Q register. Multiplicand is in B register. Multiplier sign is in QS. So now what is AS value? AS value is nothing but BS XOR of QS. Okay. So XOR operation between BS and QS will result you the result of your product, which is nothing but ES. AS. Okay. And what is the process? What is sequence counter? You require one sequence counter. How many number of times this multiplicand need to be added to the accumulator? Okay. So sequence counter will hold n. In here, the n is nothing but 5. Okay. So now what we will do initially, we start with the Qn, which is the rightmost bit. That is nothing but the least significant bit. We'll inspect this bit first. Okay, least significant bit. If this bit is a 1, then multiplicand is added to the accumulator, which is initially 0. Okay, multiplicand is added to the accumulator, which is initially 0. After adding, what you have to do? After performing addition, what you have to do?
Right. Shift right.
Shift right side by 1 bit. So combinedly, a Q register forms the 10-bit register. This is n bit, this is n bit, 2 n-bit register. A Q register combinedly shifted right side by 1 bit. Okay, what happened? Whatever is the bit that is inspected in the multiplier, that will be comes out of its position. Now the second bit will be in its Qnth place, which is always inspecting. Am I clear? And sequence counter
Yes,
is reduced by 1. 4. Since it is not 0, again the rightmost bit available in Q is inspected always. Okay. If this bit is 1, then multiplicand is added to accumulator, which is only holds the 5-bit values. Okay. Whichever crosses, that will be occupied in your Q register as most significant bits successively. Okay. And again it shifted right side by 1. If this bit is 0, then addition will not be happened. Only shifting of right side by 1. This combined register AQ is happening every time. Whenever we are shifting this right side by 1, whatever is the extra bit to be placed in its most significant bit, so that is always 0. Okay. The extra bit that is coming inside in its most significant place of your A register is always 0, because we are talking here only the magnitude. Okay, likewise, the successively we will do till the sequence counter 0. As and when it is 0, then whatever is the values available in an A and Q register will gives us the product. And the sign is available in AS register. Okay, this is how the hardware implementation is carried out for sign magnitude data. Is this clear? Is the algorithm clear?
Yes, ma'am.
Okay. So we'll do this with the help of example. And this is the flow chart. Multiply operation. Multiplicand in B. Multiplier in Q. Okay. A holds the accumulator, which is initially 0. Please be clear. Okay. Multiplicand is in B. Multiplier is in Q. Right, your AS, which is the sign of your total product, is QS XR with BS. If both are same, it is positive. If both are opposite, then the result is negative. And what is the QS sign? Because finally A and Q register combinedly forms the product. So sign of Q is also the sign of A only. Uh, Truly speaking, we want to treat Q as a separate register at the end of the multiplication. But the QS is also here updated with the same sign of AS. Okay. And A is 0, E is also 0, and sequence counter is n minus 1. Why here n minus 1? Here we are assuming our number is of n bit width, out of which 1 bit is taken out by your sign bit, and the remaining bits whichever are available, that is what n minus 1 bit length. Okay, so hence SC is nothing but n minus 1. So here in the previous case, here these are n minus 1 number of bits, which is nothing but 5. Okay, right? So now we will every time start with the Qn least significant bit. We are inspecting that bit, whether it is 1 or 0. If it is 1, we perform addition. Okay. And whatever is the extra bit that is available, if we get any extra bit due to this addition in the form of carry, that is available in E. Okay. And that EAQ is shifted right side by 1 bit. You need to take care of this carry also. While performing addition, there may be a possibility of getting carry that has to be taken care. Otherwise, magnitude, product, we will get a wrong result. This extra bit, you should not neglect. We are not doing any 2's complement addition or not. Okay, we are just adding the partial products. Right? So EAQ has to be shifted right side. So 1 bit has been already inspected. So the sequence counter is reduced by 1, and checking for 0. If this is not reached 0, then again inspect the next subsequent bit. If it is 0, you won't perform any addition. We directly go by shifting the product EAQ and then reduce the bit by -1 and goes on continuously till SC becomes 0. As and when SC becomes 0, the product is in AQ register. Okay. And sign is available in AS. This gives you the total 10-bit result. Okay. So this is the example, whatever we have seen here manually, that we are doing with the help of example. Okay. So we'll do now example based on the time. Okay. So it is already 10:10. We'll see the example in next class. Is there any doubts here? Please kindly refer it. Meanwhile, I'll take the attendance. Tell me if you have any doubts. 5, 6, 67, 71, 74, 75. 79, 80, 86, 93, 100, 108, 110, 113, 115, 120, 120 absent every time. 7, 8, 9, 10, 11, 12. Who's this, ma? Mahendra SR Nagar, Roshita Perumalla. Please rename like others. What is your roll number, Mahendra? Okay, so absentees are 67, 71, 74, 75, 79, 80, 86, 93, 100, 108, 110, 113, 115, 120.
Ma'am, 75 present.
ఎప్పుడు వచ్చావమ్మా? ఇప్పుడు జాయిన్ అయ్యావా? మరి
No, ma'am. Roshan Parmala.
మరి మిగతా వాళ్ళని చూసి రీనేమ్ చేసుకోవాలమ్మా మీరు.
Okay, ma'am.
ఫస్ట్ క్లాసా ఏమిటి? కాదు కదా.
No, ma'am.
Okay, so rename like others. Thank you, Amma. Thank you all. Bye for today.
Thank you, ma'am.
Kindly submit the undertaking forms, please.